So today we are going to be looking at solving quadratic equations. This is in fact what we were working on for the entire unit. And much like the previous units, we are going to be seeing how we solve with multiple forms of quadratic equations. So let's talk about what this actually means and what this actually represents visually. So visually, we are going to be looking for these values here. So if I have my graph, like so. Previously, we had solved for the y-intercept, we had solved for the vertex, we had solved for the axis of symmetry. But when we are asked to solve a quadratic equation, what we're actually looking for are the x-intercepts. We are looking for the places where the graph crosses the x-axis. So these 2 points right here represent our answers. Now, just like when we were working in the last unit, we want to write those answers as points. We want to write those as an x value and a y value together. And both points will have an x value and 0. And then there will be a different x value and 0. So we're going to call this x1 and 0, and then also x2 and 0. So we see here that this problem has 2 solutions. Not every problem has 2 solutions. It's possible that we could have a different number of solutions depending on the problem. All right, so now let's take a look at the different situations when we can have different numbers of solutions. So the most common was what we just saw. The most common is what we were talking about just now, where there are 2 solutions. And remember, our graphs can open up or our graphs can open down. So in this example here, the graph opens down. But once again, we see that the red parabola crosses the x-axis in 2 locations. So there are 2 solutions for this problem. And like I said, this is the most common situation we'll see. This is probably 80 or 85% of the problems that we're going to work with in this unit. We'll have 2 solutions here. So most of the time, you are going to be looking essentially for 2 different numbers as your answer here. The next most common situation is going to be when we have 1 solution. Now, when we have 1 solution, that's because our graph only touches the x-axis in 1 location. And when that happens, it's because the vertex is on the x-axis. So for instance, I could have my vertex like this. And my vertex being the point that touches the x-axis right here. So there's only one solution in this case. So there would only be one point that we would be looking for. There would only be one number that we would need as our answer. And the point on the x-axis is the vertex. The third situation we can deal with, I'm going to erase this. The third situation we can deal with is going to be when there are no solutions. So if I have a graph like so, oh, it's frozen. If I have a parabola that looks like this, notice this parabola does not cross the x-axis. And so what we would want to say here is that there are no real solutions. And I'm going to emphasize the word real here. Because when we are working with numbers as you have worked with them before, those are what are called real numbers. However, they are not the only type of numbers that exist. There are also imaginary and complex numbers. I'm hoping we're going to have time to get into that. But there are solutions to this. There are places where this parabola crosses the x-axis, but they are not real numbers. They are complex numbers. They are essentially three-dimensional numbers that are into and out of the, like if I were writing on a chalkboard, they would be into the chalkboard and they would be coming out of the wall from the chalkboard. They would be an additional dimension that cannot be written on a flat piece of paper. So that's why we want to make sure that we say there are no real solutions here, rather than just there are no solutions, because solutions do exist, but they are not as part of the real numbers. We'll go into more detail, hopefully, with that later on this week. But for right now, that's where we're going to leave that right there. So as I said, there are three possibilities for the types of solutions that we have, or sorry, the numbers of solutions that we have. We can have two solutions. We can have one solution. And then, as I said right here, there can be no real solutions. And just like the last unit, all of the problems in this unit are essentially looking for the same thing. So all of the problems in this unit are going to be one of these three situations. Once again, in this unit, we are going to see different starting places from each of our problems, but our answers will look relatively the same from all of these. Before we get into the actual problems, I want to talk about one more thing, and that is the way problems are presented, because problems can ask you for several different things, and they all actually mean the same thing. So let's talk about the way problems are presented. Because I don't want anybody missing points on this or being confused on things like the ACT if a problem is phrased in a slightly different way. Because there are several ways, I think there's like 4 different ways that this can be phrased. First off, you could be asked to solve. So if you're asked to solve, you're asked to find the solutions. And that's another way that this could be phrased. Find the solutions. to the quadratic equation. You could be also asked to find the x-intercepts. And then lastly, you could also be asked to find the zeros. All four of these represent the same thing. All four of these are asking for the same thing. But obviously, phrasing things differently could potentially cause some confusion, could potentially cause some anxiety if you're not sure what is being asked. But all four of these represent the same thing. The way that I might phrase things might be different than the way a different math teacher would phrase things, might be slightly different than the way things are phrased on the ACT or any of the standardized tests. But all of these represent the same thing and actually represent the same process. It's like having different names for the same thing. So let's start looking at some problems, and we're going to start with the simplest. We're going to start looking at some graphing problems here. So let's draw out a graph. And obviously my graph is not going to be perfect, but I'm going to do the best that I can. And then I'm going to draw a parabola here. So you would be given a parabola on a graph similar to this one right here, and you would be asked one of the following things that I just mentioned. So in this case, you would most likely be asked, find the x-intercepts. And a lot of times it's dependent on what is presented to you, the way that the question is phrased. For instance, a problem that presents a graph is most likely going to ask you for the x-intercepts. And so all we are finding is we are finding the 2 points where our red parabola crosses the x-axis. Remember, the x-axis is the line that's going side to side. The y-axis is the line that's going up and down. So we need these 2 points right here. So what are these two values? What are these two numbers where our graph crosses the x-axis? Well, if we count from the center to these points, we see that this first one is one space over. So we are going to take this and we are going to write it as a point, not just the number 1, but we are going to write it as 1, 0, because this point is one space to the right, but it has not moved up or down at all. It's still on the x-axis, and so the y value there is going to be 0. Similarly, we can do that with this point over here. We see that this is 1, 2, 3 spaces to the right. So this would be the point +3, 0. Once again, because that point is on the x-axis, the y value is 0. It has not gone up or down at all. It is just sitting on the x-axis, and our y value is going to be 0. Whenever we are writing out our x-intercepts or our solutions, those y values will always be 0. That's not going to change. It's only the x values that change there. Questions on this example? All right, let's look at a second example. So these two, this would be our answer. We need both of those for our answer to be complete. But let's look at another example here. So you see that we have our graph, we have our parabola on the graph, and once again, we are asked to find the x-intercepts. So what do you think for this? What are the x-intercepts for this problem? It doesn't have any. It doesn't cross the x-axis. So for this problem here, we would say there are no real solutions, or there are no real x-intercepts. Can't see that. I want you to be very specific in what you write. If you write no solution, that's technically not correct. No real solution is technically correct. That word real is a very, very important word in mathematics. And so I would, once again, like to emphasize, you need to make sure that you have this word real involved if you're explaining this. Because we are, hopefully, if we've got time, going to talk about the non-real solutions that are involved in this. Because like I said, there are places where this parabola crosses the x-axis, but they involve an additional dimension. They involve 3 dimensions rather than 2 dimensions. So we want to make sure that when you are explaining this, you do include the word real here to say that there are no real solutions on this problem. All right, so now we are going to look at how we solve equations that are in factored form. And this is actually a very simple process. So when we were seeing equations or functions in factored form, the previous way that they had been written was with an f of x out front, and then something like this. So we've got parentheses, x minus 3, and then parentheses, let's say x plus 6. Yes, it does. Because all of these are different representations of quadratic equations. What we were just looking at was graphs, the graph of a quadratic equation. Now we are looking at the function representation or the equation representation of a quadratic equation. But we're still solving for the exact same thing. We're still solving for those x-intercepts, where the graph crosses the x-axis. So with this one, what we want to do first off is we need to change this f of x to 0, because if we're solving for the x-intercepts, we know that from those points, those 2 points that we see right here, the y value for those is 0. So this f of x needs to change to 0 here. So this is going to turn into 0. But the rest of the equation will stay the same. We're still going to have this x minus 3. And we're still going to have this x plus 6. But anytime we are solving a quadratic function, anytime we are looking for the x-intercepts or the zeros or any of those other phrases, we need to turn this f of x into a 0 in order to solve this out. Now, these parentheses are being multiplied together, right? If I am multiplying two things and the result is 0, what do we know about at least one of those two things? It's got to be 0, right? So what we're going to do is we're going to take each of these two things and we're going to set them equal to 0. So we're going to split this up so that I have one equation with just x minus 3, and that will be equal to 0. And then I'm going to have one equation with x plus 6 and have that equal to 0. Because if either one of these equals 0, then the whole thing is 0. So we're just assuming that both are 0. But now we have two very simple equations to solve. If I have x minus 3 equals 0 and I want to get x by itself, all I need to do is add 3 on both sides. And so then this gives me x equals positive 3. And that represents the point 3, 0. That's one of my two x-intercepts, just like we found from the graphs. For the second equation here, we would subtract 6, exactly. And so then I get x equals negative 6. Which gives me the point negative 6, 0. And that's my other x-intercept. And that's it. That's all I need to do. We found the x-intercepts for this quadratic function. We found the x-intercepts. We found the solutions, just like we did when we were looking at a graph. But obviously, this is solved out algebraically rather than graphically. All right, so this time let's have f of x equals, let's say negative 4 parentheses x plus 5 and x plus 5. So just like before, we want to turn this f of x into 0. Simpler than that for what we're doing here. But when we were working last week, what did that negative 4, what's that negative do to our graph? It makes our vertex a maximum, makes our graph open down. It doesn't actually change anything about the x-intercepts. And I'll show you why here in just a second. So that we know that we need to split things up. similar to the way that we did last time, but now we have this number that's in front of our parentheses here. I know that I can split up the two parentheses, but if I try and split up this -4 into its own equation, similar to what I'm about to do over here, if I have -4 equals 0, does the number -4 ever equal the number 0? No. So we don't have anything to solve for. There's no variable with this, so we can essentially ignore it for what we're doing. So we are not going to get any x-intercepts from that -4 right there. You could have any number in front of the parentheses, and it wouldn't change the x-intercepts. It would change other things about the graph, but not the x-intercepts. So we can really just ignore this number for this problem here. And we'll just deal with the two parentheses where the variables are. So I've got x plus 5 equals 0 for my first equation. And then I'm going to have x plus 5 equals 0 for my second equation. So what do I get when I solve these out? I get x equals -5. I get the same thing for both of them. So what does this mean if I get the same thing for both of these? How many solutions do I actually have? How many x-intercepts do I actually have? We only have one. The only x-intercept that we have is going to be -5, 0. But let's go ahead and look at one more example of this. The -4 does not affect anything in that problem right there. But let's look at a similar problem here. That might give you a better explanation of why that number doesn't affect anything. Let's have 2x parentheses x minus 12. So remember, we did see some problems in factored form that looked like this. They didn't have two parentheses, they only had one parentheses. When we were listing out a, m, and n, that was a situation where m was 0. We could have rewritten this as parentheses with +0 on the inside. So this could be rewritten as 2x, x on the inside and a 2 on the outside, and x minus 12 right here. So you could rewrite this to look like what we had previously when we were working with factored form. But I'm actually going to leave it in this original form right here. I'm not going to change my form around because I want to show you it's actually easier to work with the original form. So if we treat this similarly to the last couple of problems, I know that I need to split up. I know that I need an equation for my parentheses. So I'm going to have x minus 12 equals 0. But I also need an equation for the other x over here. So I'm going to set this 2x equals to 0. Now, if I'm solving this first equation right here, and I have 2x equals 0, what do I need to do? We need to divide. We're going to divide by 2. X is 0. So if I have a number in front of x right here, does it actually matter what number I have? No. Because we have 0 on the right side here, no matter what we divide by, we're still going to get 0. So it could be a 2 here. It could be a -4 like I had on the last problem. It could be 5,000. When I divide, I am dividing 0 by that number. And because I am dividing 0, the result will always be 0 in this situation. It's why this -4 didn't change anything about our x-intercepts. Same thing right here. If I have this 2 in front of the x and I divide by 2, I still have 0 here. So my x-intercept is still 0, 0. The second x-intercept, obviously, I'm going to add 12 on both sides, and I'm going to get x equals 12. And so my second x-intercept will be 12, 0. So if these ones are making sense, you're in a really good position, because what we're going to see later on in the unit is we are going to learn how to put things into factored form in order to solve them out. So for example, eventually we will be looking at starting in standard form. For instance, f of x. Yes, we should write this down. We're going to start in standard form. This will be later on in the unit, probably either the end of next week or a little bit afterwards, depending on how quickly we get through things. We say we have f of x equals x squared plus 5x plus 6. And you may have seen some factoring, but we were definitely going to be talking about it here together. We are going to learn how we turn this standard form into factored form. And so we would have f of x equals x plus 2 and x plus 3 as a simple example here. That would then let us solve this out just like we saw. So eventually we are going to be adding some steps on the beginning of the problems that we had seen today. So this would eventually give us our x-intercepts of -2, 0 and -3, 0. So eventually we'll be turning standard form into vertex form, or sorry, into factored form, which will let us solve for our x-intercepts here. Standard form is generally going to be the most tedious of the forms that we are going to look at. We will not look at that until next week at the earliest, but we are going to have several different methods for solving when problems are in standard form, because factoring doesn't work for all of them. But we'll talk more about that later.